Okay, so let's do another example here. In the World War One, German soldiers had a sort of an experimental idea to avoid being killed by bullets, and that is they would sew steel plates into their uniform shirts. And so the idea would be a bullet could ricochet off the steel plate. Now, the question is, what kind of force did that exert onto them? Okay, so let's consider a bullet, a 15-gram bullet, moving at 285 meters per second. It ricochets off, and when it ricochets off, the velocity is going to be equal to well, let's actually say it's 385 meters per second coming in. So this is a high velocity bullet. Ricochets off at 365 meters per second. And so the question is, what is the force exerted on the chest of the soldier? Well, we know that the average force is going to be the impulse over the time interval. So that's the change of momentum over the time interval. So we need to know how long does it take for this impact to happen. So let's say that the ricochet, as the bullet comes in, so as the bullet comes in, it deforms a little bit and ricochets off. So let's say the time interval is going to be 1.5 milliseconds. Okay, so this is the initial velocity. This is the final velocity. Well, the initial velocity is negative because it's going in a different direction than the positive. So the change of momentum is going to be P final minus P initial over time. Okay, and so the force is going to be mv final minus mv initial over the time interval. So that's going to be m v final minus v initial over the time. And so that would be the average force would be the 0.015 kilograms times v final 365 meters per second minus a negative 385 meters per second, and divide that by 0.0015 seconds. And so the average force comes out to be 7.5 kilonewtons. Now that's an enormous amount of force, which actually blunt force trauma caused internal bleeding and actually caused a higher incidence of death from internal injuries than actually a bullet, which may have gone through and through. And so that's why they quit using the steel plates in uniform as a form of body. Well, the idea, though, of body armor has resurrected, except now what happens is we have a Kevlar vest. And so what happens is the bullet comes in and it's captured in the vest. So there's no recoil. Okay, the other thing is the vest gives. And so what that does is it changes how long it takes to stop. So now the delta T might be 4.8 milliseconds. Now the velocity, incoming velocity, still 385 meters per second. The mass is still going to be about 15 grams. So now the average force will be the change in momentum over the time. So that's just going to be mv. The final momentum is 0 over delta t. Okay, and so what this does for us is it gives us 0.015 kilograms times 385 meters per second, and then divide by 0.0048 seconds. So now the average force has dropped to about 1.2 kilonewtons. So now we have a substantial drop, like a 6-fold drop in the force delivered. Okay, and because it's flexible, it distributes the force more uniformly. Doesn't mean you don't get a bruise or you can't still get internal injuries, but it does change things a little bit. Now you could even do one step further and put a crushable ceramic piece in front of that, which takes extra time to stop, Okay, so that would increase this further, and it would actually slow the velocity as it impacted the vest. And so that would even further reduce the force to the soldier. And so that's the idea of modern ballistic armor, personal armor. So that's something. Now the same thing works with tank armor, and that is that they'd have tank armor. Incoming round would come in and would try to penetrate this. And so what happened was that they realized that one thing you could do is you could have sloped armor, and then it would ricochet off in that direction. And when it does, only this component of the velocity or the momentum matters. So now you put your X and Y axis like that, and you only have that component. So the more sloped the armor, then the thinner it would have to be to protect the tank. And so this was a big deal, for example, between British tanks and American tanks. American tanks in World War II sat taller and had to have thicker armor to protect them, as well as the British tanks, which were sitting a little closer to the ground and had more sloped armor. And so, again, these are the kind of ideas that go into these kind of plans right here. One other thing we can also look at, and that is recoil for a gun. So let's consider the old Thompson Submachine Gun. It was introduced in World War I, famous in this configuration by the bank robbers, of the 20s and so. Really, the military version had a stick magazine rather than the drum magazine, because the drum magazine occasionally jammed and was noisy. But the Tommy gun here had a rate of fire of 700 rounds per minute, and the muzzle velocity was 935 feet per second, so that comes out to be 285 meters per second. Now, it didn't use a full rifle round. It actually used the old-fashioned 45 ACP, the same cartridge used in the 1911 pistol, the handgun, the 45 handgun. And so that round had 15 gram bullet it fired, and the muzzle velocity was 285 meters per second. Having a longer barrel than a handgun meant that the gas had longer pushing on it, and so the muzzle velocity was actually somewhat higher than it was out of the pistol. So now I want to know, what is the average recoil force? Well, the same thing is, it's going to be the change in momentum, so over time. So we could say that each bullet comes out with a certain mass times velocity, so that'd be 15 grams, so 0.015 kilograms times 285 meters per second. So the question is, okay, then what is the average time? Well, it's 700 rounds per minute. Okay, so that means a minute is 60 seconds. So we have 60 seconds divided by 700. So that would mean it's 0.0857 seconds per round. Okay, so that means that we get that MV right there for every 0.057 seconds. So that would give you the recoil here, which would be 49.9 newtons on average. Okay, so it's averaged out. Okay. Which is actually manageable, which is why this was actually while it didn't have the takedown power of a full-on machine gun, it was manageable and easy to fire. That's why bank robbers liked it. That's why the military liked it. The Thompson submachine gun served in both world wars and even into Vietnam. And so this Korea and Vietnam. So this is actually a pretty hefty sort of thing, and it's had a lot of utility. So sometimes recoil can be a big deal. So the F-111 aardvark, which served in Vietnam, actually did not have a fixed internal weapon system, no fixed machine gun, though it did have an internal weapons bay that could have weapons interchanged in it. And one of the options was a 20 millimeter autocannon, which had so much recoil that the recoil, because it would fire so many such heavy rounds that so fast that the recoil actually exerted a force that was bigger than the engine. And so that means that when you're firing the autocannon, it would slow down the aircraft. And so that means they could only fire for a certain amount of time before they actually fired to the point that they lost so much airspeed that fall out of the air. And so that's one example of where you want to be a little bit careful.